So first of all, thank you for this nice invitation, for the warm hospitality from the Istituto Italiano di Cultura, from the Faculty of Engineering, from the department. So thank you to all the organizers of this very nice event. And first of all, I would like to start with a summary of the talk, and in particular, what I'm going to present is, first of all, brief description of the development that has led to modern mathematical economics and finance. Then I will try to explore the evolution of the role of mathematics in these two subjects. And I will try also to discuss the strength of mathematical methods, but also some challenges and some issues that have emerged in the recent years. Before starting, a couple of comments. First of all, it is clear that it is difficult to cover every relevant aspect in these topics, and so the discussion will be primarily concentrated on my skills and my interests. I am a mathematician by education, and in particular my topic is probability, so I will show you some examples from this area. And the second comment that I would like to give you is that since this talk is organized in celebration of the P-Day, which is an event aiming to raise the awareness about the importance of mathematics and its role in shaping our world, and also a way to promote mathematics and its beauty, I will try to give you some ideas of the beauty behind mathematics, in particular for some probabilistic examples in the past history. So let me start with the role of mathematics in economics. Economics, the definition of economics is far from being unanimous about scholars, even economists, mathematicians, and so on. But there is one commonly accepted definition, which is the following one. Economics is a social science that explores decision-making in the context of scarce resources. So it examines how individuals, which could be consumers, banks, institutions from government, agencies, and so on, make trade-off decisions considering the limited resources that they have. And mathematical economics, in this framework, is in general considered as an approach to economic analysis, where the economists use mathematical symbols in the treatment of economic problems, and use also familiar theorems to help with the reasoning. And in many cases, they also produce many new theorems that can help the advancement of knowledge in economics and in finance. So we can say that mathematical economics is a well-recognized field of research in economics, but nevertheless, the role of mathematics in the formulation of economic principle and result, and also in economic thinking, has been a debated topic, and we are going to see some examples about that. And this debate is still going on today. So here you can see some examples taken from the literature there are a few scholars that made some steps in the advancement of mathematical economics. I will say something about all of them. They are Cournot, which essentially is the first mathematician to try to use mathematics in economics. We have the examples of Jevons, Walras, and Menger, which are considered the father of the so-called marginal revolution. We will see something about Fisher and Pareto, who tried to introduce in economics some method taken from physics and also the language of physics. But we will also see some critiques to mathematics in economics made by Marshall and by Keynes. And finally, we will move to modern mathematical economics, which is in generally coincides in generally with the book by von Neumann and Morgenstern, and also with the research by Samuelson. So this is the idea for the first part of this talk. And so it is generally accepted that no important mathematical analysis appears in economic literature before Cournot, when he published in 1838 his book Researches and so on. So there is nothing in the literature of political economics, mercantilism, physiocracy, etc., which may be properly regarded as mathematical. In practice, the writings of the classical economists were almost entirely discursive, with the exception of a few arithmetical illustrations. With Cournot, we can see, as I said before, one of the earliest and most important tentative to use mathematics in economics. Why? Because in his work there is a strong effort to formulate the laws of economics in a rigorous way, introducing precise definitions and also mathematically proven propositions. We can give an example, and in particular the way in which he proves the existence of a maximum for the so-called profit function, which is described here. So since the demand function, which is a typical function used in economics, Fp is continuous, the function P times Fp, which expresses the total value of the quantity annually sold, must be also continuous. And since this function at first increases and then decreases as P increases, there is therefore a value which makes the function maximized, and which is the solution of the equation that you can see there, which is derived from the rule of derivative of the product of two functions. So as you can see, this is a proof simple, but containing a genuine application of mathematics to economics. And what we could say here is that mathematics essentially appears as a language, so the language of economics. A different perspective is offered by Jevons, Menger, and Walras, which, as I said before, are considered the father of the marginalist revolution, which dates back to the 80s of the 20th century. In this theory, the economic value of a good is decided by the so-called utility function, which is a measure of the degree of satisfaction or the pleasure that a consumer receives from the last marginal unit they consume. So the idea of Jevons and Varras was that the marginal utility of a good could be measured by looking at how much this utility changes when we consume a small amount of good. And in mathematical terms, this means that they are assuming that the marginal utility of a good is the first derivative with respect to the good. So you can see here the introduction of mathematical analysis concepts. So in their theory of marginal utility, mathematics emerges as a technique. So they use derivatives, they use integrals, differential and difference equations, but they also use the so-called deductive approach. They use techniques and the deductive approach to create economic mathematical models explaining various economic events and processes. In particular, for what concerns the deductive approach, we can say that this method allows for clear, rigorous, simple formulations and derivation of important relationships in economic theory. And this deductive method also led to the foundation of neoclassical theory, which still today serves as a measure framework in economic science. So the perspective here is different from the one by Cournot, because in some sense here the role of mathematics is that of a method, a set of techniques. And one effect of this mathematization of the economic discourse was that this discipline opened to contribution from other scientists, especially physicists and engineers. Fisher and Pareto were among the first to encourage not only the use of mathematics in economics, but also of mechanical terms, as I said. Their works favored the establishment of a methodology for the use of mathematics in economic research, similar to the role that rational mechanics had at the end of the 19th century. Fisher, in particular, in one of his publications, it is a nice thing because he drew up a table with mechanical analogies where particles were individuals, where space was represented or corresponding to commodity, force to marginal utility, and so on. So there is the tentative to translate in some way the language and the methods of physics into economics. Even Pareto did some consideration similar to the ones by Fisher, and in particular in one of his publications he wrote that pure economics has no better way of expressing the concrete economic phenomenon than rational mechanics as for representing the concrete mathematical one. It is at this point that there is a place for mathematics. It therefore appears quite legitimate to appeal also to mathematics for assistance in the solution of economic problems. So what we can derive from these simple examples is that there is, first of all, the ambition to recognize economics as a scientific discipline, and also with mathematics playing a role which was similar to that assumed in hard sciences like physics, for instance. However, together with these scholars, we also have some examples of important economists who offered, again, different perspective, and in particular with Marshall in 1906 in a letter that he wrote to Arthur Bowley, he invites to be more cautious about the use of mathematics in the development of economics. Because for him, mathematical tools, yes, were of great use in the task of constructing and developing a theory, but their primary use was to clarify and render consistent arguments. Along the same line, Keynes, even if he was not an enemy of mathematical analysis, he raised similar concerns. And in particular, he wrote that too large a proportion of recent mathematical economics are merely concoctions, as imprecise as the initial assumption they rest on, which allow the author to lose sight of the complexities and interdependencies of the real world in a maze of pretentious and unhelpful symbols. So the process of mathematization was not at all obvious. And in particular, we have some breakthrough with, as I said, von Neumann and Morgenstern, and in particular with the publication of the famous book Theory of Games and Economic Behavior. According to the authors, in this book, they explore fundamental questions in economic theory, addressing their precise formulation and resolution with a new level of logical rigor. And also they use mathematical methods that significantly differ from those employed by previous and contemporary mathematical economists. In particular, what they do is to derive a new economic result through a completely new mathematical topic, which is the so-called theory of games of strategy. So the idea is that we assist in this case to an intensive mathematization of economics with the use of concepts originating from several fields of mathematics, such as set theory, linear geometry, group theory, mathematical analysis, and so on. But they go one step further in some sense, because their mathematics is not only related to the use of existing tools, their use in economics, but mathematics itself becomes a way to get new insights to economics. So it becomes a way to get new knowledge in the economic framework. And in the same direction, Samuelson took the lead in applying mathematical in applying mathematics to economics. In one of his main book, Foundations, he insisted that mathematics was essential to the understanding of economics, and he also argued that mathematics should provide operationally meaningful theorems, which means that theorems should be capable of observational and empirical significance and testable in idealized conditions. So there is also an attention to the empirical side of economics, and this is the first time this attention comes out in some way. So he also argues that the language of mathematics sometimes is necessary for representing substantive problems, and that mathematical economics can lead to conceptual advancement in this subject, in this field. Okay, from Samuelson on, there has been a lot of results. Samuelson formally set the style for much mathematical economics for the following years. And the point is that, thank you very much. The point is that in these years, mathematics becomes a way to create a new knowledge. As a side remark, I would like also to stress that some literature identifies the birth of modern mathematical economics with the institution of the econometric society. Why? The reason is that the birth of such institution indicates that there is a common research program where the aim is to unify the economic theory, the mathematical analysis and statistics. And this is the first time that a common research program appears. And the emergence of econometric reflected the growing conviction, especially among the younger generation, that mathematical and statistical techniques were crucial for the advancement in the field. And we will see something about that in particular with regard to finance. However, since von Neumann and Morgenstern and Samuelson, mathematics had significantly advanced the field of economics and has become a way to transform the discipline into a more precise, predictive and rigorous field. And nevertheless, some open problems remain, and some of those problems will be described in the next part, which is concerned more with finance. So, next part is dedicated to the role of mathematics in finance. Finance, as a sub-discipline of economics, is the study of economic behavior, allocating financial or monetary resources across alternative financial instruments over time and in a risky environment. Why in a risky environment? Because financial instruments deal with the uncertainty. We don't know tomorrow what will be the value of some stock or other assets or derivatives and so on. So this uncertainty creates a framework of risk that has to be managed by those who operate in the financial sector. Familiar examples of financial instruments are bank accounts, loans, stocks, government bonds, corporate bonds, and also derivatives, which are the more complex instruments in finance. Essentially, these instruments are agreement between parties where the value of the contract depends on future prices of some underlying asset, such as a stock, a bond, a currency, and so on. Economic agents are units who buy and sell financial resources in a market with the goal of maximizing their wealth or their profit. And it is clear that in order to proceed with this maximization, several fields have to be taken into account. In particular, the tools used in financial decision-making draw from many areas such as mathematics, probability, statistical theory, and also psychology in the recent year. So, in particular, mathematics applied to finance focuses on the study, which means the introduction of new products, the pricing, the management of risk, the quantification of risk, and so on, of sophisticated financial instruments. And this has a significant impact on finance practice. And as I will try to illustrate, mathematical finance also contains some really beautiful applications of differential equations and probability theory. So one of the earliest and nicest examples of financial engineering can be traced to the philosopher Thales in ancient Greece. Aristotle tells us about a nice situation involving Thales, which is the following one. According to the story, he knew by his skill in the stars, while it was yet winter, that there would be a great harvest of olives in the coming year. So, having little money, he gave deposits for the use of olive presses, which he hired at a low price. When the harvest time came, and many wanted all at once and of a sudden to get olives, he let them out at any rate he pleased. Thus, he showed the world that philosophers can be easily rich if they like, but their ambition is another sort. So, 2050 and 500 years ago, what was trading Thales was nothing but a call option contract. That is, a contract allowing him to secure the right, not necessarily the obligation, to dispose at a future time of an asset, the olive presses, by paying a price in advance and thus making a profit in case the value of the good have increased at maturity, that is in the spring. So, as Aristotle mentioned, Thales wanted to show that his knowledge as a mathematician, also as a philosopher and an astronomer, was useful for the whole society. Another very nice example is given in the book Liber Abaci from Fibonacci, who was also mentioned before. This is a very first book containing practical problems of financial nature, and here you can see a very simple example. So the question is, how long does it take to extinguish a loan of 100 pounds at an annual rate of the 20% if it is repaid with constant annual installment of 30 pounds? Okay, this is a typical problem that we also propose to our students in our degree courses, which usually they are not able to solve. But however, this could be solved by using a simple equation where n is the unknown, the equation that you can see there, and all the other data are fit into the equation. Another important moment for the development of finance and financial mathematics can be dated back to Bernoulli, which is also an Italian scientist, scholar, which took an important step towards the so-called theory of expected utility, which is still used today in risk management and risk quantification. And the example here is the famous St. Petersburg paradox, which is described here. So Peter tosses a coin and continues to do so until it should land heads when it comes to the ground. He agrees to give Paul 1 ducat if he gets heads on the very first throw, 2 ducats if he gets it on the second, 4 if on the third, and so on, so that with each additional throw, the number of ducats he must pay is doubled. If we want to describe this situation with the language and the formalist that we use nowadays, we would probably describe the situation in this way. We have a set of scenarios, which is head or coin and head, and so on. And we have, this is the space of possible outcomes, and we have some profit according to the situation that realizes, which is 1, 2, 4, and so on, so the power of 2. And we have also the probability that each of these events realizes. So what is the point here? The point is that if you calculate the expectations, that is the average, the mean of such a game, the expectation is not finite. But the rational gambler would enter the game, any rational gambler would enter this game at any price. This could be rational because you always win something. However, the gamblers didn't want to act in that way because the value that they attributed to this game was very low with respect to the value of the whole game. And so this is the paradox that Bernoulli resolved in some sense. He gave an interpretation by introducing the so-called log utility function and supposing that the value of the game is not the average, but instead is the expectation of the logarithmic of each possible outcomes, which is a completely different way of calculating the price, the fair value of this game. The reason why you used the log utility was that this utility function has some property of diminishing marginal. In his own words, we can read, suppose we seek to determine the value of pole expectation. The determination of the value of an item must not be based on the price, but rather on the utility it yields. There is no doubt that a gain of 1,000 ducats is more significant to the power than to a rich man, so both gain are the same amount. And this seems to be the first time that an investment decision-making is evaluated according to an expected utility principle instead of an expected value. But the birth of modern mathematical finance is recognized to be the doctoral thesis of Bachelier in March 29 of 19. So Bachelier is credited with being the first person to apply the Brownian motion in finance. For those who are not familiar with the Brownian motion, we could say that this is a model that had been introduced in the 19th century to describe the movement, the motion of microscopic particles in a fluid resulting from their collision with atoms or molecules. And although the rigorous construction of the Brownian motion is due to Wiener, Bachelier was the first to define it mathematically and also to apply its trajectories for modeling stock price dynamics and calculating, as a consequence, option prices, so the price of some particular contracts. And I would like to say that most of the exciting innovations in the modern history of mathematical finance are rooted on the discovery of the Brownian motion, as I would like to show you in the next slides. So why the Brownian motion has been so successful in finance and more in general in other fields because of its many interesting properties. For instance, there you can see a picture reproducing a simulation of the Brownian motion. It is a so-called stochastic process, which is continuous but nowhere differentiable. It is defined to be self-similar in laws, which means that if you zoom in or zoom out the Brownian motion, it is still the Brownian motion. And it is one of the best known stochastic processes with stationary independent increments, which means that the evolution of this model between two intervals that are not intersecting one to the other are independent. And finally, it is a so-called martingale. That is a process for which, if you want to forecast the future value of some variable, the best approximation that you can do is the value that you have today. This is the meaning of martingale. But the Brownian motion, besides its nice features, is also one fundamental ingredient for the development of stochastic calculus and for the development of stochastic differential equations, which are particular equations where the unknown is a stochastic process and which are described by some dynamics, which contains some called deterministic part, which in some sense is connected with the average behavior of such process, and contains also a random part, a perturbation, which is also considered as the variability of the dynamics of the process around the mean. So the idea is that a stochastic process reproduces the evolution on time of some financial variable, but also biological or physical, and so on, by means of this structure. So the indication of the direction of increasing, and also by the variability that we can have around this average behavior. Stochastic differential equations are extremely used in finance for different reasons. One of them is to model stock prices, as we can observe in the geometric Brownian motion, which is a model whose illustration is reproduced here. And the idea is that it describes something that on average moves like the exponential function, but there is some variability governed by the so-called volatility. Another example is the Cox-Ingersoll-Ross model, which in general is used to describe interest rates, and processes like that have different behavior from the previous one because they exhibit what is known as long time asymptotic behavior towards an average value. So different models coming from stochastic differential equation have different applications in the financial sector, but not only in that sector. Another ingredient that produced many other processes which are important for finance is the so-called Ito lemma, which was proposed in 1951. What the Ito lemma states is represented here. It is a formula which acts for twice a differentiable function. I will not go into the detail, but the idea is that it is a really powerful formula, at least for two reasons. The first one is that it gives a way to construct and produce and also solve new stochastic differential equations from given one. And it is also considered to be a nice result because it is the counterpart of the chain rule in the Newtonian calculus. So it is the stochastic counterpart of this rule. So Brownian motion, Ito's lemma, stochastic differential equations form the foundation of stochastic calculus. And this framework is really widely applied across various sectors, physics, engineering, biology, and many other fields. And I believe that it represents one example of the beauty of mathematics, in the sense, for instance, captured by the words of Russell, where it is said that mathematics, rightly viewed, possesses not only truth, but supreme beauty. A beauty that is cold and austere, like that of a sculpture, without appeal to any part of our weaker nature, without the gorgeous trappings of painting or music, yet sublimely pure, capable of perfection, such as only the greatest art can show. And I think that this beauty can be seen in the harmony, in the elegance, in the structures of some results and some formulas that I showed you, but also many others. Also because they remind maybe to classical ideals of balance and symmetry. Another major breakthrough came in the 70s of the last century with the publication of two important papers in two important journals, a paper by Black and Scholz and a paper by Merton, where we can see the introduction of a new methodology for the evaluation of financial instruments, and in particular call options, which is based on partial differential equations. Black and Scholz equation and formula seems in some sense inevitable, like a natural law, even if it makes some very simplifying assumptions, such as constant volatility, and also even if it is wrong, as other simple models, such as linear regression in some sense are wrong in finance, this model works extremely well in practice. It is useful, it is interpretable, it is general, also because of its simplicity. And in this sense, it has rapidly become the reference point for more complex models. The best summary for the significant contribution of the Black and Scholz formula is given by Rubinstein, who says that the Black and Scholz model is widely viewed as one of the most successful in the social sciences and perhaps the most widely used formula with embedded probabilities in human history. So it is really important in the financial framework. But though based on inadequate assumptions, the innovation introduced starting from the two papers mentioned before stimulated significant expansions in the size, in the scope, in influence of finance, and in economy. in the 1995, the combined sector of finance, insurance, real estate surpassed manufacturing in terms of gross domestic product in the United States. And by the year 2000, this sector was also the leading one in profits. So this growth was partly fueled by new financial products, but also it occurred in a deregulated environment. And this has to be taken into account for the crisis that we encountered in the following years. In fact, the application of mathematical models in finance has been taken to an extreme at a certain point. So in recent past, the mathematics of the models has become so interesting on one side, but the model's ultimate scope in some sense has been lost. And an interesting description of such behavior is given in a paper by Paul Hembrecht and co-author. Paul Hembrecht is one of the most recognized mathematicians who had some administrative duties in the Basilea Committee for the vigilance of financial institutions. In this paper, he and his co-authors gave some academic assessment of the financial crisis from the point of view of mathematicians, and in particular they try to discuss where quantitative risk management went wrong. And I will try to show one of the mathematical issues that appear in the reasoning by Hembrecht. According to the authors, one of these issues is in some sense related to the famous Banach-Tarski theorem, which is a well-known paradox in mathematics. In its more folkloristic form, this theorem states that given a three-dimensional solid ball, it is possible to cut this ball in infinitely many pieces and then reassemble these pieces in order to obtain two balls of the same size. So, in other words, we could say that any solid, a P, for instance, could be partitioned in a finite number of pieces and then reassembled in order to get the sun. Okay, this is very strange. So, according to Hembrecht, this theorem has been completely misunderstood by the world of finance in the recent years, supporting the false idea that it's possible to create something out of nothing. Why? Because at that time, many financial instruments were sold on the market, and often finance and mathematical finance, financial engineering was described as magic, in some sense, magical. People compared the creation of new financial instruments to cutting a pizza into slices, putting them back together and obtaining then two pizzas of the same size as the original one. So in the language of modern finance, the second pizza is usually referred as a free lunch, where a free lunch means a situation where a person doesn't pay for goods or for services. However, as many economists usually say, if something seems to be free, there is still an hidden cost involved, which is not taken into account. And so the Banach-Tarski theorem and the idea that there is no such thing as a free lunch in some sense, contradict one to the other. So what is the issue here? We can realize a little bit more what is the issue if we think to the proof of the Banach-Tarski theorem, because this paradox can be proven within the standard mathematical framework of Zermelo-Fraenkel set theory, which is the foundation of modern mathematics. It provides a solid base for nearly all mathematical reasoning. Inside this theory, there is an axiom which is called the axiom of choice, which logicians have debated a lot, but in general, for most mathematicians, is accepted without problems, even if from these axioms come out strange results like the Banach-Tarski theorem. If we think to the proof of this theorem, then suddenly the paradox disappears. Why? Because though we have the existence of the partition of the balls, its constituents are so-called non-measurable, which means that we are not able to determine or define the volume of the pieces. So as a result, one cannot construct concretely the solution of this theorem. And so the idea of Embrecht and his co-author is that this paradox should invite us to reflect about the importance of clearly understand definitions, conclusions of any concept, the results, and also the way in which proofs proceeds. Additionally, these authors also invite to think that mathematics is, yes, precise, but the models are not, as they are only approximations to a complicated world. And more in general, technical questions like pricing, hedging, which are asked in the financial industry, often are based on highly incomplete model assumptions. First, for instance, the assumption that the market follows some known probability, or the assumptions underneath the mathematical relation between the different variables. So economics definitely, and to a high degree, finance and insurance involve an important social and human factor which cannot be fully captured by rationality and which should be taken into account when we do mathematical applications in finance. Embrecht and his co-authors then suggest that practitioners should apply the models only after careful assessment of the limitations and serious questioning of the assumptions that make a model work. Asking, for instance, what if an unexpected event occurs? Will they affect markets in a way that no mathematical model can predict? What if the regularity that all mathematical models assume ignores social and cultural variables that are not subject to mathematical analysis? On the other side, mathematicians instead have to learn what the real practical issues are all about and not put in a big mathematical hammer asking where the nail is so that they can hammer it in. So it is important to always humble in the face of real problems. This is the suggestion, at least from Embrecht and his co-author. If time permits, I would like also to give some ideas of new developments of mathematical finance. Otherwise, I can stop here. I don't know. I will try to. Okay. So Of course, nowadays we are in a new era of mathematical finance because of the introduction of artificial intelligence methods in economics and finance. This can be seen by the increasing number of publications on artificial intelligence applications in finance, and also in the fact that financial technology, or fintech as it is called, has changed the way financial resources are managed. So financial institutions have adopted these new technologies in order to trade, for portfolio management, for investment advices, for quantification of risk, and so on. And the following co-occurrence network, which is an instrument used in the review of literature, gives a visual representation of important themes in AI, mathematics, and financial management, along with their connections. As you can see here, each node represents a theme along with its average publication here. The size of each node represents the degree of occurrence of that theme, where the intensity of the link between two nodes represents the degree of two occurrences. And so what you can see, of course, is that algorithm is the theme that appear with major intensity. But also we can see that there are some terms deriving from pure mathematics, like dynamic programming, like network analysis, like optimizations, which are at the basis, in some sense, of the development of mathematics. And we can also see that the intensity of the link are focused in particular between algorithms, optimization, and genetic algorithms. So one can derive from representation, illustration like that, but also many others can be considered that mathematical and statistical modeling form the AI foundation to characterize, formulate, model, analyze, and so on, financial system and their working mechanism. However, it is clear that AI applications in finance brings up ethical issues, as it happens in many other fields, that need to be looked at carefully. I will not go into this topic because it is beyond my expertise, but I would like to show you an example where AI brought some significant progresses in mathematical research, so in a pure mathematical problem, and then I will stop. What I would like to show is an illustration on the field of nonlinear partial differential equations, which are among the most ubiquitous tools used in finance, for instance, in the Black-Scholes model, but also in optimal control theory, that is in allocation problems. And as elegant as these models are, their practical use has proven to be very limited due to dimensionality. So the computational cost for solving this type of equations in general increases exponentially with the dimension. Deep learning, in some sense, helps to reduce this computational cost. And here I show you an example of a partial differential equation, which is of the type considered here. Partial differential equations are equation involving an unknown function together with its derivatives, first derivatives, second derivatives. In general, are function of two arguments, One is time, because they describe the evolution on time of some variables, and the other one is the space variable. So a PDE is something like the formula that you can see, where the point is try to build the solution. And in particular, these kind of equations are so-called backward in time, which means you know the final state of the variable and you would like to recover all the past history of this variable. So why, how deep learning can be used in this framework? First of all, let me be precise on the fact that there is a connection between these equations and the so-called backward stochastic differential equations, which are a particular family of stochastic equations. And the idea is that we can recover the solution of the PDE starting from this BSD, where there are two unknowns. One is yt, it is in practice related to the unknown function in the PDE, and there is another process related which have some connection with the gradient of the solution of the PDE. So the idea is that we can use some deep learning techniques to construct, in this case, to be simple, the only thing to be determined is the value at the first instant, so u of 0, x0, where x0 is the initial state of our unknown function u. And how can we proceed in a very simple way? We assume that we know the initial state, so the initial function u. We also assume that we know its gradient, and in particular we assume that they are described by two parameters, theta 0 and theta depending on the gradient. We then, in some sense, consider the inverted equation for the PDE. And we compute, starting from this, we compute the value of the function at the terminal time, capital T. So we are in some sense inverting time. And how we fix a partition, and we try to approximate both the BSD, so the stochastic equation entering in our problem, and the stochastic process that can also be related to our original PDE. By this approximation, the idea is that we are able to sample the processes that are involved in these approximations, and by them we are also able, by means of a multi-layer feed-forward neural network, to construct some approximations for the gradient of our unknown variable, unknown function, by introducing some parameters. So the idea is that using feed-forward neural network, we are in some sense able to approximate the gradient of the unknown function at some fixed times, and by means of that we can take the original Brownian motion and the original process as input to give as a final output approximation of the unknown function u. At that point, as in general deep learning works, we consider the difference in matching of a given terminal condition and the approximation of our process. This difference in matching is in general called expected loss function, which depends on some parameters. Among these parameters, the first two are those describing the solution that we are looking at. so that optimizing this expected loss function, we can recover the best approximation, the best parameter theta 0, which serves as the solution of the original PDE. So this method is called deep BSD method, because with the use of deep learning and with the use of backward stochastic differential equations, we are able to solve, at least numerically, partial differential equations, and it could be proved that it works in a very general setting. It can be applied in several different areas. So this technology and many others guarantee good results to understand correlations, occurrences, trends, and therefore generally sufficient to perform a plurality of tasks, but fundamental questions about the impact of AI on economics and society still remain subject of active debate among experts. So I believe advancing this framework is one side a difficult task, but is needed in future research and its application to financial system. So thank you very much for your attention.